All right. Well, greetings. I have the top of the hour, so we're going to go ahead and get started with the webinar. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. If you're not already following me and the American Segmental Bridge Institute on LinkedIn, I'd encourage you to do so. It's where you'll find information about events like this, our webinars, and other activities that we have coming up. Hopefully you all are here today to see the webinar about spanning a landslide, design and construction of a balanced cantilever transit bridge. We have two really great presenters here today to join us, and I'll be introducing them here in just a little bit. But first, I want to do some announcements. The first is, hopefully when you registered for the monthly webinar today, you did so through either this QR code or from the link to the SurveyMonkey on our website. What this does is it pre-registers you for all of our webinars this year. And so you'll get an email each month telling you about the webinar, and you'll have the opportunity to add that then as a calendar appointment. And the advantage is you don't have to remember each month to sign up for the webinar. You'll get an automatic registration each month. So hopefully then you'll be able to join us. Our August webinar is at on the 27th, the last Wednesday of the month at 1 p.m. Eastern Time. Folks are going to be talking from AECOM about a really unique cable-stayed pedestrian bridge that they did there in Philadelphia. So again, encourage you to attend that session. I've seen this session already and I invited them to come present again because it's really, really well done and really informative opportunity. Some quick instructions then on our webinar. If you lose your connection, of course, you're going to miss content, but you can use the connection you were provided to log back in. You will then certainly be missing some of the content, and we do ask you to attend at least a minimum amount of the presentation. We're looking for, as close to the hour as possible in order to be able to issue you a PDH certificate. If you'll give us about a week to get those certificates out to you, they will arrive via email. If a little more than a week runs by, and then certainly reach out to us and we'll see what happened on your certificate. We are going to do Q&A at the end of the presentation. And the way that works is you'll have the opportunity to type in your questions during the presentation. So you don't have to wait till the very end. You can, in the dialogue, the questions pane, you can type in any questions you might have. We have a Q&A moderator who I'll introduce here in a minute who will then walk us through the questions and answers. If you're on a mobile device, you should have a little question mark in the upper right-hand corner, and you tap that, and again, you can type in any questions you might have. We will be making the recording available, as well as a PDF of the presentation will also be available on our website. But one of the other things I wanted to point you to on this particular presentation, there is in the handouts section of the go-to webinar pane an opportunity to download an ASBI magazine article that was in the winter 2025 issue of ASBI. It's a great companion article if you want to learn a little more about the project and that Sound Transit has going on. So with that, I will move to our Q&A moderator is Mr. Wade Bonzen, and he'll be joining us at the end of the session. He's the ASBI Construction Practices Work Group Chair. And he's also the Project Development Manager of Complex Bridges for GM2 Associates. So our presenters today will have two. The first is Mr. Phan, who is a senior bridge engineer for Kiewit Engineering Group with over 14 years of experience. He provides the full spectrum of engineering services for projects across the US and Canada, including through conceptual design to final design, construction engineering, and the design of temporary structures. So he kind of runs the whole gamut of work there for Kiewit. And then our other presenter today is Ian McPherran, who's a project manager and has been with the company for more than 17 years, During that time, he's worked on several cable stay and balanced cantilever projects in the U.S. and Canada. So again, a great resource to be part of this presentation today. And so with that, I'm ahead of myself. Let's ask Thanh to become the presenter. And Ian is saying he can't hear anything on his end.
I'm good now, Greg.
You're good now? Okay.
Yep.
Excellent. All right, so we're moving. All right, Thanh, we can see your slides, and the floor is yours.
Okay, thanks, Greg. Good morning, everyone, or afternoon, depending where you are. Thanks, Greg and ASBI, for having us here today. As Greg said earlier, our presentation is titled Spanning a Landslide, Design and Construction of a Balanced Cantilever Transit Bridge. So for today's presentation, I'll start with the project overview, and then I'll put on my geotech hat and discuss the liquefiable soil that we had to contend with on this structure. I'll then go over a few alternate technical structure types that we investigated before landing on the long span structure itself. I'll then hand it over to Ian to cover the various aspects of what we called construction-driven design, and then we'll end the presentation with some time lapses and some photos. So let's start with the project overview. The project is called the Federal Way Link Extension Project, or F200 for short. It is located in the greater Seattle metro area and is an extension of Sound Transit's existing regional light rail system. It starts where the line currently ends at Angle Lake Station, which is located just south of Seattle-Tacoma International Airport, for those who are not familiar with the area. The project has been delivered under the design build model. The line is approximately 7.8 miles long, and it runs mostly adjacent to Interstate 5 and terminates downtown Federal Way. This presentation will focus on Structure C itself, as highlighted in red right there. It's located in the city of Kent, and it's approximately in the middle of the alignment. So zooming into Structure C there, the structure starts just north of South 259th Place, and the whole structure is approximately shy of 1,500 foot in length. The initial portion, which is approximately 400 feet, uses precast pre-stretched girders. The second portion, which is the focus of today's presentation, is the cast-in-place balanced cantilever structure. One thing I want to point out is the bridge, the structure itself was designed by Kiewit Engineering, and the contractor was Kiewit Infrastructure. So Kiewit did everything. So let's talk geotech for a little bit here. Taking a longitudinal section through the structure, we can see the main span is set to clear a liquefiable soil zone, which is that red layer that we're showing on the screen. Okay, so what? People put foundations in liquefiable soil all the time. So why do we need to span it? So taking a cross section through the zone, we can see the embankment on the left, which is holding up southbound Interstate 5. It's approximately 50 feet tall. The uncompacted fill layer underneath, which is the liquefiable zone shown previously, is very soft. And in an earthquake, this layer will liquefy and cause the embankment to slide downhill. In other words, we end up with a lateral spread event. Then you can see there the embankment is also prone to slope failure, which occurred a couple of times during the life of the project. The two pictures on the slide here shows the slope failure that occurred while the team was out installing timber piles for a temporary construction access road. So before landing on a long span structure, we investigated a few other alternates that I will go over in the next few slides. These alternates fall into three separate categories. First is to improve or to strengthen the existing ground. The second one is to remove and replace the uncompacted fill layer discussed earlier and replace it with competent material. The third was to make the foundation strong enough to resist flow demands. So I'll go over each one and every one of these here in the next few slides. So for the ground improvement, soil strengthening was considered through either deep soil mixing or jet grouting. Either one of these techniques essentially pumps a cementitious slurry into the ground to strengthen it. This concept was ultimately abandoned due to various environmental and technical concerns. These techniques typically create a lot of spoil that must be contained. These spoils are full of cementitious fluid and other environmentally sensitive materials. The ground improvement area required would also be too large. The picture on the right shows the ground improvement zone extending beyond the right-of-way limits that we had. Even with these large areas, geotechnical analysis shows there's excessive shear strain in the seismic event, and the soil improvement block would fail. So the next concept was to remove and replace. The idea was to excavate, remove the liquefiable soil material, and fill it back up with competent fill. First, soldier piles and tiebacks would be installed in an attempt to temporarily support the existing embankment. Next, we would excavate out and remove the liquefiable material, and then we'll fill it back with competent fill and to build a bridge foundation. Taking a longitudinal section through this concept, these remove and replace zones would be approximately 250 to 300 foot apart. The structure type for this would have to be a steel plate girder of sort. This option was really abandoned due to temporary excavation, and to construct the construction zone must be extended beyond the transitway limit or the right-of-way limit into I-5 and washdowns right away. This requires revision to the agreement and a host of other permits challenges. Furthermore, this construction would require large cranes and a big laydown areas. It's very challenging in a narrow right-of-way corridor that we had with the existing slope. And shoring towers would be needed on the slope and would pose additional risk due to the soft embankment. So the next concept we looked at was what we call foundation strengthening. The first one is the large diameter caisson concept. The caisson will be constructed out of a series of secant piles arranged in like a radial pattern to create a circle. The soil inside the circle will be replaced and filled with concrete to create like a flat bottom. Column would be built on top of that platform and so forth. Two of these piers will be placed inside of the liquefiable soil zone and with approximately 170-foot spans. This option was abandoned because the landslide load would grow with the large circular diameter, so you end up chasing your tail with larger demands and larger capacities. And there are also a lot of construction risk with this. These secant piles would be very, very deep, and these shafts may wander as you build them. Staying with this foundation and strengthening theme, the last technical alternate we looked at was the strong piers with isolated superstructures. These piers have a smaller longitudinal width than the caisson, so that addresses the load versus capacity concern. This option would also come with isolated superstructure that sits on the sliding bearings that can slide in both directions. This structure would consist of post-tension splice girder that are approximately 190-foot long spans. We took the strong pier option through final design and released it for construction actually, but with other alternates, it all goes back to the unstable slope. The equipment was mobilized to temporarily stabilize the slope to provide construction access, and the slope slid. The ground is simply too soft. So when this happened, we, in coordination with Sound Transit, went back and took a step back to assess our options, and it was collectively determined that the long span balanced cantilever structure with this top-down construction to span the slope was ultimately the right path forward. So let's dive a little deeper into the long span structure here. The 500-foot long main span was sufficiently clear the lateral flow zone that I discussed previously. The 300-foot back spans also provide the adequate clearance for a future fist passage that WashDOT intends to build And then, as I discussed before, balanced cantilever construction is top down to avoid impacting the embankment. So let's take a closer look at the detail of the structure. The segments are set to be 11.5 foot long for the deeper segments and 15.5 foot long for the shallower ones. These segment lengths were set on purpose based on the capacity of an existing set of foam travelers that Kiewit already owns. That Ian will discuss that a little bit later. At the two cantilevers, we use twin walls to address the out of balance moment with the half segment offset. The north column shown in the left picture there supports both the back span of the balanced cantilever and the last girder span. The south column, not shown, supports a short jump span that takes the structure onto an MSA embankment. For seismic purposes, locked up devices, or shock transmission units, as we call them here, are used to engage the two end columns in an earthquake while allowing the bridge to expand and contract under thermal creeping shrinkage. Looking at the section of the structure, the box is relatively narrow, and it's just under 29 foot wide. It's designed to support 2 tracks with OCS in between the tracks. You can see the plethora of cantilever tendons there. And the box is 25 foot tall at the pier and 12.5 foot tall at midspan. The construction sequence for this structure is pretty typical to what one would see for a balanced cantilever structure. After site prep, the large tangent piles, wall to hold back the embankment near the foundation are built, and substructure construction can begin. For the structure, we supported each blade column on a single large shaft. For this site, it was more advantageous to build larger but fewer foundations. This also eliminated the footing, like shaft cap, that we simply didn't have room for. And the mono shafts provided the additional flexibility that we need for seismic, given how low the structure is to the ground. After the columns are built, the pier tables are poured, and foam travelers are erected to get ready for segment casting. Segments are cast in balanced cantilever fashion, alternating between backspan and mainspan. For this project, we decided to make backspan closure first. This provided construction team with access from both the north and the south side. After backspan closure, mainspan travelers are manipulated out of the way to make room for the mainspan closure itself. Prior to mainspan closure, we jacked the structure apart towards the target displacement. We calculated the force and monitored it in the field as we were doing the jacking operation. So after mainspan closure, the bridge was ready for track and systems and other related activities. And then the STUs are also installed. So with that, I'll hand it over to Ian to discuss our approach of construction-driven design.
Thanks, Thanh. So I'm going to spend the second half of the session talking about basically the integration of our design team, the KIE team, and then with our construction team throughout the whole process. And along the way, kind of give several examples that highlight the work getting built. As Thanh mentioned, we consider this a construction-driven design. Basically, can you go back a slide? Basically, a progressive design build approach. As Thanh mentioned, this was a design build project, but this was a change in the middle of that project and kind of became a progressive where we had to advance design and keep construction going. This project delivery method is becoming more popular in the industry, and just recently living it, we really saw a lot of success in the build out, the design and the build out of this bridge. We're going to cover kind of several aspects of that. Next slide. So on the erection manual, nothing, earth shattering here. It's the first place where we started with, and so the phase shown on the slide, for example, is what Tons group developed for the drawings, and then we advanced that with the erection manual, which was authored by McNary Bergeron. So it gives you the specific steps to set up and secure the form traveler, It gave us our survey and geometry control steps, and then it also incorporated all the weight durations and strength requirements for tendon stressing and form stripping. So kind of with that theme in mind, we started this really early on and engaged McNary and KIE all working together at the 30% design stage. And so we had a draft direction manual that we kept advancing. This kind of engaged everyone early and helped shape both the bridge design and then also a lot of the temporary structures that we're going to talk about. Next slide. So one of the most significant efforts we spent in this process was integrating design and construction was the choice on the project to do integrated shop drawings for the whole segmental bridge. So these weren't required by project specs, but we elected to produce these basically as a means to ensure construction success. We were under extreme schedule pressures, and we wanted to do as much as we could in advance of construction starting to vet out all the problems. We would definitely say, looking back, this really paid off in all the ways we wanted it to pay off, and also a bunch of unanticipated benefits. So this started with pulling up an old example that IBT had done from the SR20 floating bridge segmental work. We kind of used that as a template from the last time we'd seen it done, and then innovated a little bit on what the whole team wanted to see. We had the rebar supplier and the post-tensioning supplier on board, and brainstormed what all we wanted to be in these integrated shop drawings, what was the purpose. And so the goal that we all set was we wanted each segment to have a single 2D package of literally every piece of information you needed to build the segment, all in one work pack, like a 12-page pack to build that one single segment. So all the concrete dimensions so we could lay out all the formwork, all of the rebar informations, bar lists, bend diagrams, all of the post-tensioning duct callouts and sweeps and inflection points, all of the stressing data right there, anticipated elongations, all the different layouts for embeds, so traveler sleeves, the rail embeds are for the plinths, everything for embeds for the handrail, things for the closure, all of that. And what that equaled was about 68 separate packages for all the different segments plus the pier tables. We subcontracted with Sistra IBT to be the owner of producing these shop drawings. And Sistra's method for this is to model each segment to 100% accuracy in 3D using MicroStation, and then basically study for and identify all of the conflicts, rebar to rebar, rebar to PT, rebar to an insert, and so on. And so all those conflicts were either resolved by IBT through known guidelines or bubbled up to Tons Group to review and resolve the conflict in 3D. A big benefit was that Sister IBT was also the independent bridge reviewer for the permanent design, so they're very familiar with all the structure. And then KIE would also review the 3D model as well as the future 2D drawings. So then once the 3D model was fully complete and everybody had bought off on that, then 2D packages were generated with rebar bar lists, the post-tensioning data, all the other information. And so ultimately there was 68 of these 2D packages that also act as a final as-built, and then those were submitted to Sound Transit for approval prior to starting construction. A big key to success of this effort was starting early. We assembled and started drafting these before the final bridge design was even completed. And it was a full-time effort for IBT Sistra for about a year to get the whole thing done, and really came down to the wire on a couple of the final segments because construction was catching up with the process of generating these. Next slide. So the 3D model incorporated all elements of the segment, so formwork, traveler tie-down sleeves, like I mentioned, and then all the conflicts resolved. Like sleeve locations were dropped into the rebar and PT layers, and then like for most worlds, the traveler sleeve location governed and everything got moved around it. You can see kind of some of the congestion and some of the examples there. The detailing accuracy was about an 1/8 inch or better, which is higher than say rebar tolerance for fabrication or placement. People kind of had the old assumption that, well, it works on paper, it works in a 3D model, but it's never going to work in the field. And we found quite the opposite with the modeling that was done. We really came to trust that if the model was conflict-free, that everything would fit, and we really saw that out in the field. Everybody having the same set of drawings. I think it's a testament to the modeling that was done, and really truly chasing down every single conflict. If we did find conflicts that existed, and in many cases it was found that the work wasn't built right. It wasn't that the model or the drawings was wrong. It was something had been layered incorrectly, or some rebar had been bent not quite right, and that was the issue versus the actual drawing set. Everyone on site had a copy of the drawings, even our inspectors, and even folks wanted the 3D model to understand a lot of the complicated geometry. You could bisect it by layer and see all the details. Next slide. These are just more examples now of the 2D drawings that were produced. Just really easy, clean packages with all the information. So top left would be concrete dimensions, the bar lists are in there, all the PT information kind of on the right. And then just, again, everything in one spot for everyone to be able to use, and then a really great record for the end of the project. Next slide. So after integrated shop drawings, the second most significant effort, kind of integrating the design and construction team, was all the temporary works involved in the long span bridge. I'd say why these typically don't involve the permanent bridge designer. They might be done all after the fact when the bridge is all done designing it. On this type of technical bridge and under the schedule we were under, the permanent designer's involvement was really critical, and it really helped the success of all the temp structures working the way we wanted them to. Now, we teamed with 6 different design firms to help spread the load and get expertise on each of the areas. Design, like the design firms included McNary Bergeron, SMG, some of the other ones I'll mention here. So looking at the list there, the big ones, false work and form work. I'll talk about some of our equipment and access roads, all the closure, jacking that Thanh mentioned, all had engineered jacking beams. A lot of our big shaft cages needed significant rebar stability checks, a lot of critical crane picks, worker access, all those sorts of things came to play. And then another key is many of these designers came on site or spent time on site inspecting their work or their design as it was built, making sure it followed the design, really helped fast track making sure that element was done and ready for the next phase. And then I'd say similar to the integrated shop drawings, we started all these temp designs really early. I think almost every single one of them started before the permanent design was stamped. Next slide. The very first temporary design that was started, kind of the most important, was the travelers, formwork travelers. This was actually started during the conceptual design phase of the bridge. Thanh needed the traveler loading to start some of that early construction sequencing in their models. And so we teamed with McNary Bergeron to design the formwork traveler. For the history folks on the call, this formwork traveler was not new. It was something that Kiewit purchased back in 2011 from an East Coast contractor, and we used it on the Tillicum crossing down in Portland, Oregon, which was a cable stay cast in place segmental bridge. And then following that project, these travelers went out to Hawaii and they constructed many, many miles of segmental transit guideways on Farrington and Kamehameha projects for HART. And then following those projects, they were brought back to Washington, made available for this project. For the long span, McNary basically recreated and rechecked the old Parkin engineering design for these travelers, and then identified a bunch of unique modifications that were needed for these travelers to work on our segments. The travelers also had a lot of wear and tear from all the years of use. And so we had to do quite a bit of assessment and repairs in the shop to get these ready to go. Finally, shown on the right is the formwork itself that hangs inside the Traveler or from the Traveler. We did this separately with Smith Monroe Gray, and just another coordination element to get everything to work together, the formwork hanging correctly and all the right design assumptions, along with the EOR to make sure everything meets up. Next slide. Couple flashy photos of the yellow Travelers being assembled onto the pier table. I want to highlight the decision that we made early on in the design phase on the pier table size. We wanted to make sure it was large enough to erect both Travelers back to back. Again, from a schedule standpoint, making sure we could get quickly started on segment casting to reach the closures. Really helps jumpstart the work and then help with the pier table false work. We assembled 4 identical Travelers, so we were casting on all 4 headings at once to finish as fast as we could. Next slide. Ton highlighted in the early photos of the site. The bridge was built in a really narrow footprint, the wetland on one side and then the freeway right on the other. And so the integrated team basically strived to develop one temporary access concept that would work for all phases of construction. So we wanted the same access to work for drilled shafts that we ultimately needed for, say, removing the formwork Travelers. KIE designed a pretty extensive system of soldier pile and lagging walls that were cut into the hillside by the freeway, and then a bunch of hill thicker wire basket walls that went along the wetland border and provided us with basically a 30-foot wide road along the whole side of the bridge to work from. And then we had basically pockets in the hillside at each of the piers. These are really risky temporary designs given the poor soil conditions that Ton highlighted. And as Ton highlighted, we utilized timber piles in sections where we had the really heavy drilled shaft crawler crane loads. Ultimately very successful. This access worked for everyone involved. It was really the premium, easiest way to get to work on all points of the work. And then ultimately all these elements were removed and the hillside was restored to a landscaped embankment that you'll see at the end. Next slide. I mentioned earlier one of the biggest false work systems that we utilized was for the pier table, support the bottom, and then all the formwork for the walls and the top. This was designed by McPherran, and to overcome the poor soil conditions that were right on the outskirts of these pier tables, we collaborated on a false work system that was supported on the top of the permanent drilled shafts with steel posts that basically hugged onto the columns. And then a big network of steel grillage was utilized off these posts to cantilever, create a dance floor, and basically fill in that pocket in the hillside. We provided our access and then support for all the formwork to cast the pier tables in 3 different stages. Next slide. In addition to authoring the erection manual, McNary also authored the bridge geometry control manual. And so this manual identifies and numbers the several hundred different phases of segment casting that can be then used to track, to control geometry of the bridge during the build. And the manual identified the physical targets points for each segment. And in total, we tracked about 248 phases from the end of column construction all the way through the closure. Next slide. The bridge geometry was recorded basically every single day during segment casting. We were casting 1 to 2 segments a week. And we called the early morning surveys globals, as the surveyors with total stations would collect as-built data, station offset elevation across every single segment across the whole cantilever. And then the control points were survey nails installed in the leading edge. That raw data was imported directly into a spreadsheet developed by McNary, and then that compared the as-built bridge shape from that morning to the theoretical shape from the erection manual. And the comparison could be studied point by point or in summary graphs like you see on the screen. The sheet also had the ability to then produce target points for the next segment to set the formwork for the following day. We had a full-time Kiewit engineering group designer who managed basically the survey schedule, all the data input, and then coordinated with McNary real time to look at the results and then set up the targets for the next segment. Overall, our casting accuracy to the base design was really just really well tracked and some of the best we've seen in terms of per spec from our experience on segmental work. Next slide. Jumping topics, and kind of on the theme of really starting early and overlapping with design was the mixed design development for concrete. We started this about 14 months ahead of construction, so really right when the design was starting. And our internal Kiewit engineering group started developing different mix designs working with the local suppliers. Our target mix segment strength was 8,000 PSI at 90 days for the permanent design, but our construction schedule was built around the mix's early strength gains. So we were targeting to achieve 3,500 PSI in 18 hours. That was what the goal that we started with. Besides those two criteria, we also needed a mix that met or exceeded a 100-year design life for durability. Trying to chase after that perfect mix, we lab trialed about 15 mix designs with Corliss, our concrete supplier, and then we truck trialed about 7 of those, and we finally narrowed it down to 2 different mixes. One was a type 1L and one was a type 3 that both got approved for use on the project. Primarily the 1L was used for all the segment casting. Ultimately, we achieved our goal. We're getting a really consistent 3,500 PSI in 18 hours that allowed us to proceed with stressing the post-tensioning and then moving the traveler. So overall, huge success. Our mixed design did not let us down in terms of our tight schedule. Next slide. Along the same themes, the concrete is the thermal control that goes with it. So our same group does some great modeling to look at this. Really with this high performing, high early strength concrete mix came a ton of heat generation during the curing process. So the team developed a bunch of models and looked at the different segment pores, especially the pier tables with some really thick elements on the slabs and the diaphragms. These things looked at varying insulation on the formwork, varying ambient temps, different concrete delivery temps, and basically all modeling to see where we were at versus the spec required max heat, which was 185 degrees. Many of the models predicted we would come dangerously close or exceed that max. And so we started with modeling the introduction of cooling tubes, cold water cooling tubes throughout the pores. To implement this in the field, we put together a cold water system consisting of an industrial water chiller there on the right, a big reservoir tank, a big pump, and then a bunch of manifolds and a network of this clear PEX pipe that ran in the grid pattern. The graph illustrates an output from the exact system that we used for thermal tracking. Several days of the cure period where you can see the concrete peak and then cool and staying below our max temps with use of the cooling system. Next slide. Unlike kind of many projects that get designed with kind of a generic PT system, similar theme here, we selected Schwager Davis early on to get kind of maximum input and efficiency on the design and then to jumpstart all that integrated shop drawing work. Really worked really well in terms of having all their CAD files, knowing all the materials, having all the exact specific dimensions to run at everything and come up with a conflict-free segment design. Many of the unique details were developed along the way to lead to successful PT installation, down to the details of where did we route the grout tubes, and in this case routed them up into the bridge curbs, which really helped with preventing water from getting in the ducts during construction. One additional collaboration element was that the EOR tons group performed the tendon elongation calculations. That's something that may be typically assigned to the PT supplier. Tons group used the Midas models to output the elongations, and then McNary with their model for their extra manual, and then SDI reviewed and did a second check. In the field, we experienced actual elongations basically exactly to the EOR's model, kind of proving out the system. And then the photos highlight some stressing of the continuity tendons inside the pier table, and then some of the duct up in our segments. Next slide. The final really proof of the integrated design and construction, and the final big lift was the segmental closures that Thanh mentioned. So these had really tricky phasing and kind of staging of every single task. They had a lot of temporary works, form work, jacking beams, portions of the traveler remaining behind, permanent design assumptions for all the alignment forces, and then finally all the continuity tendons, bottom slab, PT stressing, all had to be sequenced and done perfectly. So we really started this closure planning again back in the design phase. We optimized it several different times. We saw issues where it was gonna mess with our schedule, and changed it several different times, and ultimately found a pretty good solution. The photo on the left is inside the box that shows the closure formwork in place, and then it's kind of a low profile system, and then you've got the large continuity tendons staged. Those are ready to stress within 8 hours of the concrete being placed in that closure. And then the photo on the right, an aerial looking down at the backspan closure jacking system of steel beams that was in place, ready to stress when the concrete was placed. Next slide. So I've said it a bunch of times now, that design integrated with construction, and it sounds great. It sounds like it could probably happen remotely, kind of in today's market, but what really made it a success here, not just that it happened, but that it happened with a ton of folks on site at the bridge. We had a lot of design folks there day to day, from the geotech engineers that were out, viewing all of the drilling operations, a bunch of staff supporting the superstructure rebar, the PT. I mentioned the geometry control. Basically had designer presence on site the whole time. And my thoughts from the contractor side is, as a designer, you really saw like there's nothing better than seeing the work, carrying buckets of grout like that middle photo, to really see what you're designing and what all the triggers are, what matters. So very, very successful with the team approach and the design staff on site. Next slide. We have 2 time-lapse videos for you guys. This is of the pier table completed. See if this works to play. Pier table completed with the traveler erected, and I think it's skipping maybe a little bit for folks, but jumping out towards the mid-span closure is what you see, and then one of the travelers coming off and the mid-span closure being cast. Next slide, Thanh. And then this is a video that starts with some of the pier tables again from a different perspective. Shows the backspan being cast, a small section that we didn't talk about that was cast on false work, and then ultimately the backspan closure occurring. before the midspan. Next slide. And then this slide highlights present day. So this was taken about a week ago, and basically landscaping underneath the bridge is wrapping up. Full speed train testing across the bridge has pretty much occurred completely and is behind us. And this whole 7-8 mile alignment of new transit is set to open to public ridership by the end of this year. Overall, really challenging project with all the changes that Thanh talked about, all the geotechnical risks and setbacks that we had. Really had a lot of problems to overcome. But the selection of the long span, and then the integration of the whole design team, construction team, everything that we mentioned on all those topics, ended up allowing us to finish the project actually several months early, the bridge, and then finishing within budget. So overall, kind of a success across the board. We're happy we got a chance to talk about. Next slide. That's it. We open up for questions.
All right, thank you, Wade.
Okay, great.
Ask you to step in. Yeah.
Absolutely. Thank you, Ian. Thank you, Thanh. Good presentation. Really interesting project. Kind of a unique usage of segmental technology. Got a variety of questions here, so we'll just start going through these. With the number of cantilever tenon ducts in the top deck, how was the interaction taken care of with the anchorages, you know, for track plinths and, you know, all the sort of light rail track hardware and stuff?
Thanh, you want to take that one?
Yeah, sure. So what we did is we actually use form savers that are cast with the segments, and those are anchored in the slab, obviously. And then we detail all of those and located all of those for the plinths with the integrated shops. And then after everything is built, we came back and we essentially install like a splice bar into those form savers and then bent them into place to provide that, the proper bar for the plinths. So no post install of anything.
Okay, great. Would you say that you guys weren't over live traffic here, but would you guys say that the traveler construction method is suitable for use over live traffic? And if so, what kind of special considerations would need to be thought about in that case?
Yeah, I'll take this one. So no, we weren't ever casting over live traffic, but I would say we treated it like we were, in that we did have a lot of work underneath our travelers, you know, our active access road and all those sorts of things. And so, you know, we didn't even want to drop something on top of ourselves, right? And so everything on the traveler kind of has its place. That whole bottom deck gets fully netted, and you're looking to seal all the little crevices and cracks, and that's a full-time kind of job because that traveler is made to be adjustable. And as you move forward, you know, during a launch, it all gets kind of opened up, and then once you're done with the launch, you want to close it all and seal all those gaps. And so we treated it the same. And then my other comment would be, you know, this traveler, when it was used over in Hawaii, it went over one of the freeways there and was casting segments over multiple freeway lanes for many months, many segments. So they took the same approach. It's fully enclosable with a lot of eyes and maintenance to make sure it stays fully closed and contained, but it's set up to do that. Yep.
Yep, that's been my experience too. And you're able to build over railroads and other sensitive infrastructure as well without too much trouble. So, all right, go back to the 3D modeling for the integrated shop drawings. You know, one of the challenges is that the rebar fabrication has its own tolerances. So when they were putting together those 3D models, you said everything was modeled to within about an eighth of an inch or so, but how did the rebar fabrication tolerances get accounted for?
So I'm gonna kind of elaborate on the question a little bit, or maybe dive in. Is one of the things we did, I mentioned that 520 floating bridge project. It had integrated shop drawings, and that was back 10 years ago or more. And one of the, those were the first drawings that we had as a basis. And we started asking a lot of questions like, were these successful? What did we like about them? What didn't we like about them? And the feedback from the rebar supplier, which was Harris, was like, hey, these were all modeled in 3D, all this effort was put in, but then we had to do like the old school hand entry to bend the bars. And so we really need if we could basically be integrated into the process where whatever that model outputs would go into our auto bending system. And so knowing that all sounded like, yeah, that makes sense, right? That's really smart to try to do. And so we did a trial segment really early on. We built just one segment in space in 3D, and then kind of went through the whole process and figured out what output, in this case, we use CMC. What output did CMC want? What file structure? All of that. I think it was called an RDX file is what their system used. And I think Harris uses something different. Everybody maybe has different ones, but we figured out the one that worked, and we ran several trials where they would run it through their auto bender. And we found out that certain shape codes with rebar would bend a bar that looked nothing like the drawings. And then other ones were almost perfect, right? And so a bunch of trial and error that went into that, but ultimately kind of worked out the kinks. And so every segment that IBT produced, they would have the 2D drawings, the 3D model, and then they would have this RDX file that CMC could use. And I'd say it was generally successful. I think there was to the question of like tolerances, there were issues where bars came out that were bent with the auto bender using the program, and they just didn't, when you put a tape on them, they just didn't have the right bends. They weren't quite perfect, and we really needed some perfection based on our conflict resolution. And so, I would say it was a challenge, particularly in the peer table, but they made some kind of custom tweaks to the RDX file, and ultimately we were producing segment after segment where there was, no rejected bar, no field bending, any of that. It was, ultimately pretty successful. I'd say the rebar bend tolerance was kind of overcome through trial and error.
Do you feel like the auto bending system was more reliable in terms of getting bars to a tighter tolerance?
That's my understanding. I mean, especially with some adjustments, that's my understanding. We went to the shop a few times and we're working on some of the kinks. There was bars, in the integrated shop drawings that were graduated, like in the walls of the segments where the segment's getting shorter over its length, where every single bar was a custom bar. It was bar A was this long and bar B was an 1/8 inch shorter and bar C was a 1/4 inch shorter, and kind of frustrated the rebar supplier. But with the computer program and the auto bending, it really didn't matter. They didn't care as much, right? They weren't just trying to produce 40 of the same bar. Does that answer the question?
Yeah, no, that's great. Good information. All right. Why were the backspan closure done first before the main span closure? Any particular reason there?
Want to take that one, Ton?
Yeah, so we did it primarily to provide Ian's team with the proper access, because you recall the site is so narrow. So we make backspan closures first. We can access the rest of the bridge from either side, which is what advantageous. So.
Okay, good. Can you guys comment on the cost a little bit? What was your cost for the bridge?
I was just in the neighborhood of just over $100 million. And again, with every cost thing, you got to make sure we're talking apples to apples. So that included design cost, All the temporary engineering, all those things. It also included though, like everything underneath and around the bridge. So all the civil grading and landscaping, and there was a permanent access road underneath there. But yeah, just north of $100 million.
And that included all your temporary works and soil nail walls and all that stuff too, right?
Yep, and that also was kind of all in with all the markups, indirect staff, everything.
Okay, great. Did you do any pre-assembly of your rebar cages for the segments?
We did not. We did some pre-assembly of the pier table walls, where we would assemble a wall mat and then fly it into position. Really on the segments, I think there was like, I want to say 6,000 pounds of bar per segment, somewhere in that neighborhood, and that it could get tied in about a shift. They got it down to, and so that was their preference, to just go get the rebar up on deck and just go knock it out on that cantilever, and then go bounce to the next one. I think our Traveler wasn't really set up to go. You could go bring in a couple bars at a time, but it wasn't really set up like open on the front to go slide in a whole segment type of thing. I think you could do it with maybe a different Traveler scenario. So all stick built.
Yep. Okay. Did you have any issues with cracking in the bottom slab, especially thermal cracking, that kind of stuff? How did your thermal gradient and mass concrete issues work in terms of being effective?
Very effective. We never had a temperature overage that we needed to even talk about or look at. Is this a leave as is? Is this a monitor for cracks? Or that cooling system really worked well and didn't ever go over. And then in terms of cracking, never had any significant cracking, anything really needing any major repairs, nothing structural.
Okay, great. What was the observed relationship between the post-tensioning friction and the wobble coefficient? I think what we're looking for here is how are your theoretical numbers for wobble and friction compared to how it turned out in the field?
Thanh, you want to take that one?
Yeah, it was generally good for the most part. It varied a little bit as we got out further and further on, but it was, the vast majority of it was within the allowed 7% plus or minus by specs.
Okay, great. In my experience, the shorter cantilever tendons, that are within the pier table and maybe the first couple of typical segments, sometimes we tend to overestimate the losses due to wobble. Did you see higher elongations for those first couple sets of cantilever tendons?
Yeah, it was generally perfect or slightly more elongation. So yeah, we concur.
Yeah. Okay. Good. Was there any cathodic protection for the PT systems?
The blow-in.
The ground. Are we talking about grounding?
Yeah.
Or
yeah.
the whole PT system? Yeah, the whole thing had a lot. There was a whole grounding system. All the PT anchor heads were grounded. There was a whole grounding system that ran back to the piers and down into the shafts, and then every segment was individually grounded back to the last, and there was a bunch of continuity welding. So rebar, certain longitudinal rebar in the top deck, was welded on every single transverse bar with tack welds. And then in addition to that, there was a grounding of the outside, I'll call it handrail or guardrail on the outside of the bridge back into the deck as well. so quite a network of different grids of grounding all the way ultimately back into the shafts.
Yeah, that sounds like a pretty significant system. Was that required in the original design build contract document? Or was that something that came about during the development of the segmental bridge itself?
Ton, you can correct me if I'm wrong, but it was original to kind of all of Sound Transit's guideway bridges. So even on the simply supported girder decks, it was the same thing where the guardrail was grounded, and then there was longitudinal runs of continuity welding on the top mat that ultimately went back into the columns and shafts.
Yeah, that's correct. It's a project requirement throughout.
Got it. Okay, good. How was the vibration and dynamic movement for this particular structure? Did you have to do anything special there to, you know, make sure that that behavior was within the specs needed for the light rail system?
Yeah, we certainly did. For a structure of this magnitude and a span length, we were certainly weren't meeting the 2.5 hertz requirement that are typically seen. So we did perform a complete vibration analysis, taking into account the suspension characteristics of Sound Transit's train. And it
Did you need to tweak
checked out.
Okay, so you just did a more detailed analysis, but it was still within the required specs.
Yeah, that's correct. Yeah, for a bridge of this magnitude, this kind of mass, we ran that check, and it met the requirements pretty comfortably.
Great. Okay. Okay. So, did you have seismic isolation casings for the foundations?
We had what the WashDOT calls the inspection silos, but yeah, essentially we needed to make the columns a little longer to get some better seismic performance.
Okay, great. What was the distance that the ready mix trucks needed to travel to get to each placement, and how did you guys actually transport the concrete to the formwork itself?
So that supplier I mentioned, Corliss, we have the benefit that they were local to basically one town over. So I'd say a max 30-minute round trip, or excuse me, 30-minute one way to us, and then back to the plant. Pretty much all of the concrete was poured pump truck right into the segment. We were very fortunate with that 30-foot road that we looked at along the side of the bridge to basically pull up and pump. Obviously, with bridges over rivers and things like that, we get much more ornate into pumping from one pump to another, or a line pump and a placing boom and all those things. And so that was a massive benefit, and really simplified the day of the pour, just pulling up basically right alongside it.
Yeah, that's nice having that access road and being relatively close to the ground. Makes life a little easier for concrete placement. Did you guys have any concentration issues, especially in the market areas?
No, nothing to speak of. No major rock pocket repairs. Just little bubbling at the stem walls and things like that. But we had very, very vertical walls, like in the segment cross section. They weren't laid back at like a 45, which helped a lot, and just a robust vibration plan and dedication. So no major rock pockets.
Great. You may have mentioned it, but what software was used for calculating the elongations for the post-tensioning?
We ran it through our global model and we used Midas.
And did you use Midas for the time-dependent analysis for the segmental bridge erection?
Yes.
Okay. What was the overall construction duration?
Overall, full bridge, help me out, time. It was roughly, there was some starts and stops, so that's why it's taken me a minute. Probably about 2 years, kind of overall, start of shafts to finish, maybe a little
Yeah.
closer to 18 months.
Mhm.
Okay. And then out of that process, could you give an estimate of how long it took to build the superstructure?
Yeah, so we cast our first segment in January and we cast the closures in July. So it was basically, I can call it 7 months, or I could argue 6 months to cast out the 64 segments.
Got it. Okay. So how many pours per week are you averaging for your form travelers?
We were at least one segment a week, if not two. We were on like we got down to like a 4-day cycle time on a single traveler.
Got it. Okay. You mentioned that you had some critical crane picks. Were any interesting challenges there? Was the condition of your access road such that it was okay for those critical crane picks? What were the challenges there?
Yeah, so the critical crane picks were primarily the drilled shaft rebar cages and just the drilled shaft work in general with an oscillator. And kind of the beauty of the design was that all of that was all focused right at the pier, which was outside of that poor soil zone. And so at that big pocket in the hillside where the pier was, the two drilled shafts were, really that's the ground that got really improved. So it was I don't know, it was probably 250 feet by 250 foot pad focused right on the pier, and that was all covered in crane mats, and there was some timber pile, and really a robust system right there. And then those cranes effectively didn't work outside of that. They worked there or they left. And so when we like tripped rebar cages for the shafts, those were 110 feet long, 11-foot diameter. The cage would get delivered by truck kind of down the hillside and then get tripped right at the pier and put into position with those cranes. So that was the biggest picks that we did.
Interesting. Yeah, sometimes we focus so much on the superstructure we forget how much of a challenge the substructure can be, the foundations. Did you guys design for Cooper E80 train loads? And if not, do you see that this type of bridge structure would be applicable to heavy rail?
We did not. We designed it for light rail transit loads only. But I guess if you're for the second part of your question, I don't see why not, right?
Yep, there have been heavy rail applications for segmental, certainly. All right, we're kind of running a little long here, so just a couple of questions here to finish us out. Did you ever give any consideration to casting your back spans on false work and just doing unidirectional cantilever for the main spans?
We did. It comes down to, although the soils on the back end were not as bad as the main span, they still weren't very good, and you still had to contend with the hillside. So you really weren't looking at anything near flat level ground on the whole backspan. And so kind of with a combination of those things, we certainly looked at it. We certainly looked at the feasibility, pros and cons. But for those two main reasons, it would require a lot of maybe temp walls or some sort of temp foundations for that false work on the slope. Found that, hey, we have the travelers available. We think we can be as efficient on schedule and whatnot to just do it the traditional.
Got it. Yeah, that makes sense. At what point during the design build development process was the liquefiable layer identified? Was this something that was known prior to the bid phase, the proposal phase, or was this something that was found later when you guys were doing additional borings?
This was found later. It was found during the design process of the, I guess, the original scheme, which was just a simple guideway on precast girders. So that's how the job was bid and envisioned kind of by all parties. And so through the post-bid borings, we found that the water table was significantly higher than anticipated by all parties. And then this liquefiable zone, this very succinct pocket of roughly 500 feet and right at the toe of the freeway, was all kind of uncovered along the way. And so that's some of the stuff that Ton highlighted. We needed to pivot. It was a change to the project, and we needed to pivot and go down this whole alternate design analysis path, come up with all sorts of solutions, and then vet through them and price them and schedule them, and overall see how they fit into the overall project, for the best outcome, which ultimately was the long span.
Great, fantastic. Well, again, thank you guys for a really interesting presentation, and I've got a lot of questions here from folks, so obviously very interesting for everybody that's listening today. With that, Greg, I'll turn it back to you.
Well, thank you guys. Yeah, great presentation, and appreciate to those who let us run a little long on Q&A. It's always good when we have a great discussion after the presentation. Again, as a reminder, give us about a week to get your certificate to you. We'll be posting up a link to the recording from today, as well as the PDF of the slides. And also reminder to grab out of the handouts the Aspire article, and hopefully you're already subscribed to Aspire Bridge Magazine. QR code on screen will get you signed up for the rest of the webinars the rest of the year. So with that, we will sign off, and we'll see you next month.
Thank you.
Thank you, everybody.